Come back. Today's goal of this lecture. In my previous video, I had seen what is the product topology. I had seen product topology is Cartesian product of finite set. And in my previous video, I had seen the basis description and sub-basis description of product topology. Today's goal of this lecture, today I will see generalize of arbitrary Cartesian product. In my previous video I had seen the finite Cartesian product and I had seen basis description and a sub-basis description of finite Cartesian product. Today I will see the generalize of finite Cartesian product. Here today I will see the arbitrary Cartesian product, and when arbitrary Cartesian product, then there exists new topology, box topology. When the arbitrary Cartesian product, then product topology and box topology both are different. But in finite case, product topology and box topology both are same. So today's goal of this lecture, today I will see when the arbitrary Cartesian product exists. That means there exists two topological space, product and box. Also, the basis for finite product topology and for infinite product topology both are different. Now also I will see how look like the basis in box topology. This is today's goal of this lecture. That means today I will see actually the arbitrary Cartesian product. In finite case, product and box both are same. Basis, sub-basis both are same. Okay? Let's see. That means today's goal of this lecture, product topology and box topology. And if x tau x and y tau y be two topological space, then the product topology is x cross y. And in my previous video I had seen the basis description and sub-basis description of product topology. Today's goal of this lecture, today I will see generalize of this procedure. That means I will see arbitrary Cartesian product. Consider x alpha where alpha belongs to j, because here the arbitrary Cartesian product j is the index. Then x alpha tau alpha. Product of alpha belongs to j x alpha. This is product topology. And infinite product of tau alpha, where this alpha belongs to j. This is the box topology. That means when infinite product of only the topological space, then this is product topology. And when infinite product of this tau alpha, collection of, that means tau alpha means we all of us know tau alpha is collection of open set where obviously alpha belongs to j, since this is the infinite. That means when infinite product of open set, then this is nothing but this is the box topology. I hope my all viewers have understood what is the product topology and what is the box topology when arbitrary Cartesian product. When finite Cartesian product, then product topology and box topology both are same. At first, just as a review, let's see how look like the basis description and sub-basis description of product topology. Then I will see the arbitrary for arbitrary case. In product topology, bases are look like u cross v, where u is a open in x and v is a open in y. Then the topology generated by this type of basis on x cross y called the product topology, we all of us know. Also sub-bases are pi x inverse u where u is open in x. This is look like those type projection map. If this set is u, then pi x inverse u means x y belongs to x cross y such that pi x y equal to x belongs to u. Since here y absent, that means y is arbitrary, and this is u cross x. Similarly, pi inverse v would be x, those xy belongs to x cross y such that pi y xy equal to y. Here since x absent, if this is v, then this is v cross y, and since pi x inverse u and pi y inverse u v, this is belongs to tau, so they are intersection of pi x inverse u intersection pi x inverse u intersection pi x y inverse v, this is belongs to tau, and this intersection means this part with a subbasis. That means subbasis are pi x inverse u where u is open in x, union pi inverse v where v is open in y. This is the subbasis, and the topology, product topology is generated by this subbasis also, and this is actually same as the basis b when the product topology is finite. That means similarly, if we take any finite Cartesian product x1 x2 xn such that this is contain x1 x2 xn where xi belongs to capital Xi for all I equal to 1 to n, then we can define a basis beta x1 x2 xn equal to u1 u2 u3 up to un where ui belongs to tau I where I equal to 1 to n. Then these beta x1 x2 xn generates a product topology on x1 cross x2 cross xn. Similarly, the subbasis description means pi 1 inverse u1 union pi 2 inverse u2 where u2 belongs to tau 2 up to pi 2 inverse un where un belongs to tau n. This is where this pi I means obviously projection map means pi I equal to x1 x2 xn map to xi where for all I equal to 1 to up to n. Then this is the subbasis description. This is also generate the product topology. That means these and these are same, but this is not same when arbitrary Cartesian product. This is today's goal of this lecture. Cartesian product means xn tau n be the countable infinite family of topological space. Then x1 cross x2 cross xn equal to n equal to 1 to infinity xn or n belongs to natural number xn. Then this is the infinite topological space means arbitrary family of topological space means this is the infinite strict type. Then there is two topological space, product and box, when box and when product. This is our goal of today's lecture. Let X alpha be index family of topological space. Consider the product space alpha belongs to J X alpha with the topology generated by basis. Here topology generated by collection of product of open set. Product of alpha belongs to J U alpha where U alpha be open in X alpha. This is the product of product space with box topology. The arbitrary Cartesian product, then box topology generated by collection of Cartesian product of open set in X alpha. Few minutes ago I have seen this is the basis of product topology when the space is finite. But when space is infinite, when arbitrary collection of Cartesian product, then this type of basis always generated the box topology but not product topology. When arbitrary collection of topological space, then basis for product topology is script S equal to union beta belongs to J S beta, and this is called subbasis, and by this subbasis generate the product topology. Therefore, the topology generated by subbasis script S is called product topology on the product space. That means tau equal to here arbitrary union of finite intersection of element in script S. I hope my all viewers have understood clearly. Okay. And product topology when arbitrary space, then this is generated by this type of subbasis, where this is the collection of inverse image of projection map. When finite product topology be finite, then this is obviously in finite case this is also be the subbasis of product topology. This is generate the product topological space. But when the topological space is finite, this is also be the basis for product topology. But here for infinite case, this is basis for box topology. Here the difference between product topology and box topology for infinite. Product topology alpha belongs to J x alpha. And consider denote RW, which is R cross R cross R cross, so on. This is n belongs to natural number product, n belongs to natural number xn, where xn equal to R. And consider the mapping F from R to RW with the box topology. Consider the mapping. Here tau b is the box topology, denote the box topology, and the mapping is ft equal to t comma t comma t, so on. Is this mapping is continuous in this box topology? Few minutes ago I have said box topology is generated by collection of open set. That means here u equal to minus 1 comma 1 cross minus half comma half up to minus 1 over n comma 1 over n, so on. This is, and this u equal to n belongs to natural number un. That means this is equal to n equal to 1 to infinity un, where each un equal to minus 1 over n comma 1 over n. Here the basis is n belongs to natural number u alpha, where those u alpha belongs to tau alpha. This is a basis for a topology on the arbitrary product space alpha belongs to J x alpha. I hope my all viewers have understood this is clearly. And this mapping is not continuous because we all of us note the definition of continuity. Inverse image of open set is open. Here if inverse u equal to those t belongs to R such that ft belongs to u. That means t belongs to R such that t comma t comma t, so on, belongs to u. and which is actually n equal to 1 to infinity minus 1 over n comma 1. This is actually t belongs to real number such that modulus of t less than 1 over n, and this is singleton set 0, and singleton set 0 is not open in R. So here I have got inverse image of open set is not open. So the function in box topology be not continuous. I hope my all viewers have understood this is clearly. Okay. Next I will say one continuous function in product topology. Here y equal to r and z equal to n. For n belongs to natural number xn equal to r, and product topology is n belongs to natural number rw. And here function define f from r to rw and tau. Here tau is product topology, and the function is defined as ft equal to f1t, f2t, f2t up to fnt so on, and this is equal to tt up to t so on. This is the is this function is continuous in product topology? This is my question. At first just think own self. This is very easy. The product topology. So product topology is generated by this type of subbasis element, and any open set in this subbasis element, since S alpha is equal to inverse image of projection map, this open set actually the member of this X, because this is the inverse image. So each open set is actually the member of this function. Let U belongs to script S. That means since U belongs to script S means U belongs to one particular script S alpha for some alpha belongs to J. That means there exists, since S alpha means P inverse alpha U alpha, where U alpha belongs to tau alpha, there exists U alpha belongs to tau alpha prime, such that U equal to P alpha inverse U alpha. To prove that inverse image of this subbasis open set, that means inverse image of P alpha inverse U alpha, this is the open set in X. Here we have to prove. And P alpha composition F inverse U alpha means F inverse U alpha, because if there exists a mapping F from Y to projection mapping, projection beta belongs to J, X beta means for each beta belongs to J, P projection mapping PB F Y means F of Y means X alpha, and PB X alpha means X beta, and X beta is nothing but this is F beta Y. So by these rules, this is P alpha F inverse U alpha means F inverse U alpha. I hope my all viewers have understood. And F inverse U alpha means this is the open set of F, and we all of us know in projection mapping is continuous when each F alpha is continuous. Here F inverse U alpha means F inverse of this particular point, since this is the projection mapping, so each component big always continuous. So obviously F inverse U alpha be F inverse open U alpha, since continuous, that means this is open set, because continuous means inverse image of open set is always open. So obviously F inverse U alpha is open, and this is true because in projection mapping each f alpha, when each f alpha continuous, then f is continuous. Therefore, now let's come back our original question. Here ft equal to t comma t, where the topological space is product topological space. Since this is defined in product topology. In product topology means projection mapping, and we all of us know in projection mapping, if each component be continuous, then f alpha be continuous. Here f1t equal to t, f2t equal to t, this is the identity function. So each function be continuous. So each component since continuous, so in product topology, this function is a continuous function. But in box topology, this function is not continuous function. I hope my all viewers have understood what is the box topology, what is difference between box topology and product topology, how look like the basis and subbasis member of product topology and box topology. Okay. I will stop here. I hope my all viewers have understood clearly what is the product topology, what is the box topology, what is difference between box and product topology. Okay. See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.